Sorry about that again.
No worries.
There we go.
Okay. Now it's actually working. So yeah, so in these structured output prediction problems, the output space is very large and often combinatorial, and it's hopeless to expect to find the exact correct output y for a given x. And it's often very difficult to even find a single answer. So for example, consider the utterance sale, and you may transcribe this utterance as S-A-L-E or transcribe it as S-A-I-L. And both of these transcriptions are consistent with the utterance, but a transcription that assigns the same probability to S-A-L-L and S-A-I-E is doing a bad job, and it's not modeling the conditional dependencies or the correlations in the output space. So one way to tackle search in these high-dimensional spaces is by learning patterns among the output variables to remove some of the options in the prediction and only learn the distribution among the patterns that are reasonable. So we are learning a mapping into a manifold of outputs that's not just random sequences of characters, and knowing the exact manifold helps us resolving these ambiguities. So this leads us to a general framework where we learn a joint representation of inputs and outputs to learn patterns among the output variables and between inputs and outputs, rather than just learning input representations and learning correlations with the outputs. Now in this case, our neural network takes as input both x and y and assigns a score s of x and y to the combination. And we have many examples of this joint representation of inputs and outputs in CRFs, MRFs, sequence-to-sequence models, wavenets, and deep value networks that I'll be talking about. And you may also hear the term energy-based, where the energy is the negative of a score function. Now, at inference, given a score function that ranks different output configurations, we'd like to find the argmax y of the score. And this creates some challenges between the expressivity of the models and the tractability of inference. So we gotta be aware of the inference challenges once we build more complex models. Now there are two families of approaches for tackling this joint representation learning. In one category of techniques, we try to do a ranking of different outputs, and our goal is for the correct configuration y star to have the largest score compared to any other output y. And this results in a form of a contrastive learning where we try to increase the score of the correct target and decrease the score of any incorrect target. There is another family of techniques which are probabilistic, and they try to learn the distribution of y given x, and we can take our score function, exponentiate, and normalize to get the conditional distribution. We often use conditional log likelihood for training the probabilistic models. So I'll talk about both of these families of techniques for structured output prediction. Now, to be a bit more clear about the problem that we are tackling, we have an input x, we have a correct target output y star, and the output space is large, finding y star is difficult, and therefore, we perform evaluation based on a task-specific reward function. So for our test set of inputs and outputs, we compare the predictions of the model with the correct targets in terms of a loss function L of y and y star that looks at the similarity between y and y star, or equivalently, we look at the reward function that scores different output configurations. Just to be more concrete, let's, for example, consider multi-label classification where the input is an image and the output is a binary label representing different tags for this image. And let's say the task reward is a F1 score that looks at the intersection and the union of the set of predicted tags and the set of correct tags. Another example is image segmentation. The output is, again, a binary vector representing whether a pixel belongs to a particular category or not. And we often use intersection over union as the reward metric here. Again, it's represented as a function of union and intersection between the target set and the predicted set. I'd like to start by going through the structural SVM formulation in more detail. And structural SVM presents an elegant formulation for learning linear functions for the linear score functions in a joint input and output feature space. So we first gotta define our joint feature space psi of x and y, and this joint feature space may be based on a graphical model that looks at whether two variables are equal or different. It can also look at counts and other patterns in the output space y. It can also look at the patterns between x and y. But the main constraint is that it has to be a linear function of psi x and y. And at inference, we have to do the argmax again. Now, the key observation made by Tasker et al. And Sochanderitis et al. Is that we can have an upper bound on the loss of our prediction y hat and target configuration y star in the following form. So let me try to convince you that this upper bound is correct. Here we are taking a max over all possible output configurations, one of which is y hat. If we substitute one y hat into this max, this core terms cancel out, and we are left with the left-hand side. Now, keep in mind that we are taking a max over all of configurations, one of which is y hat, so this is an upper bound. We can go a step further and note that the score for y hat is actually the largest score, so it gotta be larger than the score of x and y star, and hence we have the last upper bound. Now, what's nice about this is that summing over all the training examples, we can sum over the right-hand side and have an upper bound which is convex in the parameters. I leave that as a homework to prove that this is going to be convex. Now, this is very nice, and the natural question is, in the era of deep learning, how can we generalize a structural SVM formulation? So in this case, we wouldn't have a predefined feature of inputs and outputs, but we would learn the feature jointly with this core function. So we have a neural network that takes input x and output y and builds more abstract representations going forward. We again would have to do this inference by finding the argmax. And for training this model using the upper bound that I described, we would have to find the most violated constraints, or also called loss augmented inference, where we would have to find a configuration Y that has a large score and a large loss. And we can try to do this in deep networks as well by realizing that maybe if we relax the output Y to be continuous, we can do local inference by doing gradient descent on the input. So having access to a score function, we can start with an initialization of output Y. We can solve the inference by finding the argmax, and we can solve loss augmented inference by doing gradient descent on this objective as well. And we can do training this way. But it's unclear how tight this upper bound is, and we've already lost the convexity of the upper bound moving to neural networks. Moreover, we have these over-parameterized neural networks that are very data hungry, and we may as well go directly and regress the score function to the negative loss. So this was the key idea behind our work. I would really think of this as a baseline for all of our structured prediction work. And it's inspired by previous work in RL, where for each state, we try to learn a Q function that evaluates the score of, or the value of that state. And we often train these models using squared loss. Now, this is the way inference would be done. We run our score evaluation for an initialization of output Y. In the case of semantic segmentation, we initialize the mask at 0. Then we take the gradient of the value estimate with respect to inputs and take several gradient steps, take several more gradient steps, and we reach a configuration of outputs that has the largest score. Now, this is familiar from previous work on deep dreaming and style transfer. So this is the way we would do inference. And what's nice about it is that we can perform parallel iterative refinement. If we have lots of random variables in the output space, we can update them all at the same time, and depending on how complex the task is, it may take few steps or several steps to reach a very good configuration. I'd like to contrast this with the autoregressive way of solving the inference, where we have a sequential dependency or linear dependency with the number of output variables. And it's not very GPU friendly because the order of computation is linear. Now, in order for us to be able to do this gradient-based inference, we would have to relax our outputs to live in a continuous space. So for the tasks that I described, multi-level classification and semantic segmentation, the output was a binary vector. So we relaxed that to be a continuous vector that lives within a hypercube. We also relaxed the notion of intersection and union to the continuous domain. The natural relaxation of union would be a sum of min across the dimensions, because min is taking an and, right? And a natural generalization of union would be taking the max, because max is doing an or. And one key observation of our work is that given this relaxation, both intersection over union and F1 scores are quasi-concave. Again, I leave this as a homework. You can show that the space of output configurations that have a value larger than any epsilon is a convex set. Now, given this observation, we ask ourselves, what if we did iterative refinement on the reward metric itself? Well, because it's quasi-concave, we would reach the optimal configuration Y star eventually. But then at inference time, we wouldn't have access to this reward function because we don't have access to the configuration Y star. Otherwise, we wouldn't even do any inference, right? And the key idea is, let's learn a score function to approximate the reward landscape everywhere. And so we define our score function again that takes an input and an output configuration, and we try to learn the parameters of this score function to be identical to the reward function in all of the output space. Okay, so we define the loss in terms of the discrepancy between our score values and reward values. And again, this is reminiscence of the way people do reinforcement learning in the value-based approaches. Now, in order for computing this discrepancy, we have to select a bunch of points on which we would measure the discrepancy. And I'll talk about the set of points in the next slide. But basically, our objective becomes a sum over the set of Y configurations that we care about of the discrepancy between the score function and the reward function. And training can be done using gradient descent. We just have to have a bunch of output candidates to train on. And we evaluated several different sensible ways of generating output configurations. One, we want the value estimate to be very precise on the inference trajectory. So at training time, we can do inference again, starting from a random initialization or a particular initialization and following the gradient of the score function with respect to inputs to produce more training data for this regression objective. We can also make sure that the score estimate is accurate on the target configuration Y star. We can sample a bunch of points in the vicinity of the output configuration Y star to make sure that the score is accurate in that neighborhood, given that we may end up in that part of the space when we are doing a good job at inference. And also we can find difficult cases on which the discrepancy between the score function and the reward function is very large. And this is somewhat similar to loss augmented inference, but in a slightly different way. And the experiments are done on a very simple segmentation task where we have 32 by 32 RGB inputs and 32 by 32 binary outputs, and we only have 200 training images and 128 test images. First, we did an ablation study of different output candidate generation strategies. We thought that we should include the inference in whatever scheme that we work on, not including the examples on the inference trajectory hurt the performance quite a bit. So we compare different combinations of inference with ground truth, stratified sampling, and adversarial cases, and we find that training on the difficult cases by this hard negative mining is the best for the segmentation task. So we decided that we would only do inference candidates and adversarial candidates. And here I show you some examples of the segmentation on Weismann horses. The middle column shows the input. On the left, we see 30 steps of gradient descent with respect to inputs. And on the far right, you see the residual between the predictions of the model and the target output. And you see that at the beginning, it's kind of diffuse, but ultimately, it finds the correct pixels. In the bottom case, the head of the horse isn't well segmented from the background, but because of the strong prior that we learn about shapes, we are able to do a good job at segmenting that horse. In the top case, we missed the right leg of the horse, but the model somehow combines the other legs to create a reasonable explanation of the image, which is ultimately what we want to do with these structured models. We want to find plausible segmentations with four legs, even if they are not correct. And I like the bottom case because supposedly during training, the model hasn't seen a lot of horses that have a head on the ground. And in this case, the model somehow combines pixels from the background to create a fictitious head. In terms of numerical comparison, we outperform other approaches. The fully convolutional network is a feed-forward approach with a very similar architecture, and some of the bottom cases take 128 by 128 input images and even pre-train on ImageNet. But we are able to learn only using the 200 training cases. And part of the reason is that we are really learning the loss landscape. And we are learning that different predictions on the outputs is worth different amounts, even if they are all incorrect. Here is a visualization of the learned shape priors. As input, we give the mean horse image and some Gaussian noise, and the model somehow combines the noise to predict these different horses with different shapes of legs. We also perform multi-label classification on 2 standard data sets. And again, we outperform the feed-forward neural networks and some of the more complex structured output prediction methods. Now, to summarize, we presented a very simple approach to structured output prediction where we would simply regress the negative of energy or the score function to the reward. And we don't need complex unrolling strategies to have to compute the gradient of gradient. We can cache training pairs because basically we are just using the training pairs as a proxy to the whole landscape of loss and intersection over union in this case, and we can train using very few examples. Now, in contrast, there is independent work which presents inference as a end-to-end module and tries to optimize the parameters of inference by taking the gradient of the final loss and backpropagating it through the inference trajectory. This is a very interesting approach, but it would require more complex gradient estimation. It's much more costly, especially if you need a lot of inference steps to reach a good solution. Yeah?
Did you find that the inference happened faster, like in fewer gradient steps as training progressed? Like that you got to, I guess, the candidate decided to converge on?
Yeah, for sure. So at the beginning of training, the model really doesn't produce any plausible outputs, and most of the information is propagated back from the ground truth because we train in the vicinity of the ground truth always, either through the adversarial cases or directly through the stratified sampling.
I guess my question was like, I'd assume that convergence is some proposal of the mask. Like, did it get there faster, like in the later iterations? Like, I guess sort of my question is like, did it become more efficient as it became better trained?
So I guess my answer is because the value estimate is incorrect at the beginning of training, the gradients aren't really pointing in the right directions, and so I'm expecting the model to require fewer steps to reach a good solution.
That makes sense. Can I ask, why is it that you, do you think that just adversarial examples rather than, the proposed examples that it might spit out would be enough to train the the value function approximator? And if not, why not?
That's a good question. Just to be clear again, these adversarial examples are more or less the worst case examples, and we are computing the misfit between the two functions in terms of a worst case estimate, sort of like L infinity norm.
Right.
And supposedly, if you do a lot of training, that should be enough for training. But it's very cheap to train on inference trajectory. And in practice, we found that often results in much better models. But in a theoretical sense, just training on adversarial examples should be enough.
OK. Thank you.
And so one reasonable next step would be to try sparse reward functions which may not have this quasi-convex structure, and try to think about ways to apply our value network. There we have the code on GitHub too, and it also works on internet images. These are some images taken from outside of the test set, as long as the horses are facing left. Now I want to go back to the classification of different approaches into ranking and margin based and probability based. And I've already talked about one way of learning the joint score function by regressing directly to the negative loss. Now I want to talk about a set of probabilistic approaches to learn the score function. So the autoregressive approaches that are widespread nowadays assume a particular order on the output random variables, and they decompose probability of y given x as a product of probabilities, or they decompose the log probability of y given x as a sum of log probabilities for each individual output dimension given the input and previous output dimensions. Note that here again we are learning patterns among the outputs, because really our neural network consumes different prefixes from the output and tries to predict the next dimension in the output. Some examples include sequence-to-sequence learning, WaveNet, and transformer. Now, trying to reconcile these models with our score function view, this is the way that you can write the score function. So the score function is assigning a number to each output configuration, but then we have to subtract log sum exp of alternative outputs at that particular position. And what's nice about this form of score function is that we can simply exponentiate it and get the probability without any need for further marginalization. So it already is self-normalized. And so we can simply take the gradient of this and do training, which becomes a very simple classification problem where we are defining different instances, each of which has a different prefix. And so we applied autoregressive approaches to the problem of super resolution, and in this case we built on pixel CNN by Van den Oorde et al. So we assume a rasterized order for pixels. We have two heads of neural networks, one of which takes the previously generated high resolution pixels and the other takes the low resolution image and combines them to produce the next pixel in the output. Training can be done in an efficient way because we can have different masking on the higher resolution input image, but then inference is slow because again we have to do this sequential prediction. And for these models we don't need any task reward. So we can really train based on sparse reward or single output examples per inputs. I have to mention that there is some recent progress on the speeding up inference for these models. Now here I show you some outputs generated for a single input. So on the right you see 4 samples from the model for a given input. The inputs are 8 by 8 and the outputs are 32 by 32. And what's nice about learning the distribution is that we can sample from it and possibly consider a bunch of diverse outputs. For the faces, this is more interesting, and again we can produce diverse outputs. Now we compare against bicubic interpolation a nearest neighbor baseline that finds the nearest low resolution images based on L2 distance and then generates the corresponding outputs. Basically this is an exemplar based approach and a form of dictionary lookup. And we also compare with the feed forward approach where we would only train on L2 loss. We also had a version of generative adversarial networks, but obviously this is not a easy comparison because there are lots of different GANs out there. So I wouldn't look at that row too much. What we find is that in terms of PSNR, peak signal to noise ratio, and either in terms of structure similarity or multi-scale structure similarity, the feed-forward neural network performs much better than other approaches. And this is somewhat surprising in that we believe that the outputs of our model is more realistic. But in fact, this points out that for these sets of one-to-many mappings, we don't have very good evaluation metrics, because basically we have some missing details from the input, and we have no way of recovering the exact detail So we can either average out the details and produce a blurry output, which is what the L2 loss or the feed-forward neural network does, or we can produce new details that most likely don't match with the input details. And if we do that, we would get a worse PSNR or structure similarity. And this makes evaluation very difficult. This reminds me of some work that I've done on machine translation where we tried to improve BLEU score directly. And we were able to get about 1 BLEU point improvement upon the state-of-the-art models at the time. But when we were, but when we went and asked humans whether they are happier with the translation, they often preferred the old model. So it seems like for translation also, BLEU score is not a good proxy to human satisfaction. And so we did this human evaluation where we asked users which image they would guess that is coming from a camera. And I guess I can do that with you guys. Which one of the top images is coming from a camera?
Left one.
And which one of these two is coming from a camera?
The left.
So it seems like we were really lucky about this one. In this case, this is an output of our model, and this is the ground truth image. I guess in this one, it's somewhat clear that we are producing eyes that don't look like eyes. Anyway, so we were able to fool humans about 10% of the time on faces and about 28% of the time on bedrooms. And there is follow-up work from our group where they were able to push this even more and get about 35% full rate on faces. But what's really interesting to me and seeking further research is the fact that ranking based on P of y given x is not so great. So far, the examples that I showed you are by a stochastic inference where we sample from the model. But if we actually do greedy decoding, where at each pixel we ask the model which one is the most likely pixel, we get these kinds of results. And below each image, I show you what's the log probability of the model for an image. In this case, because we are discretizing the pixels, we can actually compute the exact probability rather than a density. And it seems that the model is putting a relatively, sorry, this is negative log probability. So the lower, the better, or the more likely, according to the model. So what's interesting is that in the bicubic interpolation images, even though they are very blurry, get a relatively low negative log probability, and they often get better numbers than even ground truth. And seems like our model is not able to do a good ranking of different images. So in summary, we can optimize conditional log likelihood model. We can optimize conditional log likelihood objective for locally normalized models. It's tractable and it's possibly efficient. And it can capture conditional dependencies among different output variables. But there are several shortcomings. One, the rasterized order of generating pixels is unnatural. So we really want to go back to our iterative refinement work and try to generate images in a similar fashion where all of the pixels are updated at the same time. And again, the inference is similarly sequential. and time-consuming, and most importantly, the ranking of the outputs is suboptimal, and we have to resort to stochastic prediction and try to tune the temperature of the model to get a relatively reasonable set of outputs. And this brings us back to the question of whether we really want to solve a structured output prediction by learning the probability distribution or simply by learning a ranking function. Also, I pointed out that for these one-to-many prediction problems, we don't have a Oracle metric based on which we can compare different models. So there's another avenue of research trying to improve upon metrics and even trying to, all right. So maybe I can stop here and let you ask any questions if yeah.
Do you have any follow-up work on trying beam search decoding or something else instead of greedy decoding?
So basically these results already are suggesting to me that we shouldn't even push more on the inference, and there's something going on with the ranking of the log probabilities. Now this may be because the space is really continuous and we are discretizing it in a unnatural way, but I really don't have a good explanation for this. So I'm pretty sure if we do beam search, we would even find more bad-looking faces.
More gibberish.
Yeah.
You started out by giving an example with like natural language processing and language. Obviously, there's a lot of structure in language problems, and things like speech recognition have very similar problems where you try to find very structured inputs. Does learning scoring functions or any of these kinds of techniques, have you tried it on any language problems, or in the other direction, are there things that are done in language that you think would be a good inspiration for this kind of work?
So for the language domain, we have the family of sequence-to-sequence models that are the state-of-the-art models for translation. They are basically based on this autoregressive approach of defining tractable probabilities. And so they are the standard technique for solving translation. They are also becoming more popular for speech recognition, where there's this model called listen, attend, and spell, which simply applies sequence to sequence to transcription. And these models are becoming the standard approach for inference on text domains. I want to emphasize that even in those cases, we observe that as we increase beam size, which is performing better inference for finding better scoring outputs, the performance slightly degrades, which is a less severe issue with those models, but is hinting again that maybe the ranking based on log probability is suboptimal. Yes?
Can you go back to the basic? So the log likelihood scores for the ground, like the upper ground truths and like near standards, that's also from the same model, correct?
Yeah. So the model is assigning these numbers to different output configurations.
So doesn't it seem like at least like having a better log likelihood that at least somewhat correlate with better inequality?
Sorry, so these are negative log likelihoods. So the lower is more highly probable under the model. I have to fix that in the slides. But so basically the model is assigning the highest probability to the greedy decoding cases and to the bicubic interpolation cases. And it's assigning lower probability to ground truth, nearest neighbor, and the stochastic predictions from the model itself.
So this, I mean, it kind of just hints that the model still isn't, learning, this actual manifold of the conditional dependence, right?
So I have a hand-wavy explanation for this, which is that when we optimize log probability, we only care about the absolute value for the correct target. And we don't care about how the rest of the probability mass is distributed among other outputs. So in a very high dimensional space, just optimizing log probability doesn't necessarily result in a good ranking, because the ranking is really comparing the score of different configurations, whereas log probability only cares about the absolute probability for the correct output. So basically, the model is not optimized for ranking, and unless the distribution is very simple, like in the classification case, we may not expect from the model to do a good job at ranking.
Sorry. I just had a basic question about the setup. So your reward function is the negative of your loss function, which is like something task specific, like intersection reunion or something.
So in this case, there is no reward. In this case, we only train on target outputs, and the objective is a negative conditional likelihood.
Well, I was actually referring to.
Oh, you want to talk about, okay, sorry. Yes, that's right. So that's a task specific, yeah.
And then your energy function, so at each training step, you update your energy function to better estimate your reward?
Yes.
Okay.
Yes, so we generate a bunch of output configurations, and on those examples, we try to improve the misfit between the model and the reward function.
Okay.
So basically, the visualization that I had kind of makes sense, where we are trying to find these points, these black circles on which we want to fit the two functions together.
Right, and so the input for that would be like input, like prediction pairs that you generated.
Yes.
How do you like input like bad pairs to give like a more uniform distribution of training examples? So, like, so your energy function is a function over like your entire space of inputs and possible outputs.
My energy function is a function over the entire space of inputs and outputs, right?
So,
and I can select random points in that space on which I can evaluate the energy and the reward, and I can train the parameters to make those 2 points close. Does that make sense?
yeah, so you're not just limited to what's in your training set, I guess.
So I guess for the input, we are not generating new inputs, even though that may be interesting. I guess the problem is we don't know the reward for inputs that don't appear in the training set, for which we don't have the ground truth outputs. So the inputs are limited to the training data, but the outputs are not limited to the correct ground truth segmentation masks, which is somewhat interesting because in the log likelihood training, we are limiting these points to the correct targets, and we only care about the score on those cases, whereas in this case, we just sample points anywhere from the space of binary codes. Maybe I can go back to the presentation here and talk about the last part of the lecture, and then we can open the questions once more at the end. For the last part, I want to talk about 3D geometric structure, and obviously the word is 3D, even though our convnets are kind of 2D. And the question is, how can we move beyond our convolutional neural nets and build more structure, 3D structure, into them? And another line of research would be how to build models that can be used for geometric reasoning. Let me start by asking a very simple question, which is, where does this red patch correspond to in the right chair? Obviously, as humans, we can identify that this leg is the correct correspondence with the other patch, and we have no difficulty doing this. Ideally, we want to train machine learning models that can solve for similar correspondences, and this may be a good test for how aware of the 3D structure are our statistical models. And this is somewhat going back in computer vision, where we were doing vision by detecting key points and solving for correspondence. And representations based on a sparse set of points can give us a lot of interesting view invariances that are missing in our commonness. So basically, in the process of building convolutional nets, we got rid of all of the work that was done in computer vision before, and now a lot of researchers are trying to combine the intuitions from 3D vision with more advanced statistical models. And another motivation is that correspondence is really central in computer vision. We can use correspondence for recognition, building more abstract models of objects like cats, or to solve localization by solving correspondences across multiple views of a video, or trying to do 3D shape alignment or 3D reconstruction by solving for the correspondences. And there's a lot of recent work coming out in computer vision and machine learning community where they try to solve for these correspondences across multiple types of cars, airplanes, and cats. And one limitation that's generally the case in all of these papers is that they often can perform correspondence in views that are very similar. So we are missing techniques that are able to solve for correspondences for the example of chairs that I showed you at the beginning, where you may have a lot of occlusion and a lot of movement of pixels. For example, an approach based on a 2D flow field would fail miserably in the case that we have 180 rotation, because there aren't simple flow fields that we can assign. So I'm talking about out of plane rotation, obviously. In that case, you have a lot of pixels that are being removed from the image and a lot of new pixels that are introduced. Now, the inspiration for our work is transforming autoencoder proposed by Hinton et al. In 2011. And I want to give you a quick summary of transforming autoencoders now. So let me tell you about this kind of model in the 3D case. So in all of our experiments, we work on ShapeNet, where we take two views of the same car for which we know the relative rotation and the relative transformation. Okay, so we can synthesize pairs of cars at any random relative rotation and translation. Now, transforming autoencoder layers an encoder that finds these capsules or sets of u, v, z coordinates. U and v represents the position within the image plane, and z represents the depth for the corresponding key point. Okay, so I learn an encoder that generates these pairs of detected coordinates, also called key points, and it also detects some visibility probabilities for each one of those coordinates, or possibly some aspects of the scene that's not rotating, like the color or the texture of the car. Then what we do is that we transform the coordinates given the known rotation and translation. So we can just apply a rotation operation and the translation to get our inferred key point positions in the other view. And we can build a decoder that tries to regenerate the other view based on the transformed coordinates. And the whole thing is differentiable, so I can differentiate through the encoder, decoder, and the transformation to learn a set of key points. So this is transforming autoencoder. Now these other aspects of the scene are copied without any transformation, and they are represented in this vector f. Now, when we train this model, we realize that the model is able to cheat in interesting ways by not really detecting 3D key points, by somehow using the 3D key points to represent some other aspects of the image. Let's say X, V, and Z do not have to represent a position of any pixel. They can represent color on which transformation changes in some way that the decoder can know how to reconstruct. So that's one caveat. And the other caveat is that we are training this decoder, and we may not even use it if our goal is not to do view synthesis. So the high-level intuition is that if the goal is view synthesis, this architecture makes a lot of sense. But if the goal is something else, then we are not using our capacity by training these models. And so the model that we developed is called, I guess we don't have a name yet. So in our model, we detect these key points and then transform them into the other view, but then use the same convolutional neural network to detect another set of key points for the other image and transform them to the other view, and simply use the misfit between the two sets of coordinates to train the encoder and decoder. All right, so the loss is a multi-view consistency between the detected key points in one view versus the estimate of those key points based on the other view. All right.
Where's the decoder?
There is no decoder, essentially. So you just have encoders that are trained with this multi-view consistency. How are we doing with time, by the way?
We have the room for another 10 minutes, and so you can use some of that time for the rest of the lecture and then some time for questions.
Okay. So I guess I have to rush a little bit, given some of the difficulty that we had with the setup at the beginning. But so if we just use this objective, there exists a degenerate solution, which is that all of the key points are mapped to the same point. And there is no notion of diversity for this objective. And so we think that this is a necessary condition for key points, but not a sufficient one. And makes us wonder, why do we even need key points? And that is an existential crisis that we had. And I guess there are different purposes for key points, including pose estimation, 3D shape alignment, and tracking. And there may be different sets of key points that are consistent with this multi-view definition, each of which is more suitable for one task. So there's not a single set of key points applicable to all different domains. We may want to find key points that are appropriate for a single task. And that led us to this aha moment that maybe we want an end-to-end optimization of key points for the task that we care about. Okay, so now for the task of pose estimation, we would use the two sets of detected key points in two views to reconstruct a rotation matrix. And luckily, this reconstruction is differentiable itself. So we have to do an orthogonal Procrustes problem to combine the two sets of rigid points to recover the rotation. And we can differentiate through SVD to the two sets of neural networks. So the high-level motivation here is that if we have a differentiable set of key points and a differentiable objective, why not optimize the key points in an end-to-end fashion? And some of the details you can find in the paper, but essentially on cars, airplanes, and chairs, we are able to find interesting key points that are consistent across types of cars, planes, and chairs. So maybe I show you some of these videos. Now note that these key points are 3D, and we don't model occlusion yet as part of the framework. So what we render here is a bunch of different views of the car and a set of key points detected from a single view. And what's interesting is that somehow the model is able to track missing parts of the objects in the 3D coordinates. And it's doing a consistent set of key point assignments across types. So you can look at the slides later. We also have some visualization of these 3D key points in 3D. I guess that doesn't play very well either. But this presents us to a very objective way of evaluating these models, which is basically doing what people often do in computer vision, which is annotating key points on different cars. And this is what we've done with the ShapeNet dataset. So we went out and asked users on Mechanical Turk to mark different important key points of cars based on a template given to them from Pascal 3D. And so for the supervised model, we train a key point architecture identical to ours that is trained using supervised labels. And then we use the detected key points to do pose recovery. And in our case, we do not have key point annotations, and we train everything end-to-end using a so-called end-to-end geometric reasoning. Okay? So I guess with that, I can end and say that the next step for us is to apply this to real images, think about non-rigid transformations, and possibly weakly labeled examples for which we do not know the precise relative rotation and translation. And I'd like to thank my collaborators, Michael Jigley and Anilia Angelova, Ryan Dahl, and John Schlenz, Supersorn Sue Jinakorn, Noah Snavely, and Jonathan Thompson. So we talked about different types of a structure, structuring the outputs, using two families of models, ranking-based and probability-based, and we talked about end-to-end discovery of key points. All right, thank you. So I guess if there are some burning questions at the end, yes.
I have a question about the segmentation example.
Yes.
So you looked at fairly small images, so like 32 by 32.
Yeah.
If I remember correctly.
Yeah.
In which case, when there's like when some of the images are like poor resolution, then having like some prior structure or understanding of the outputs can help you outperform like some of the conventional approaches. I was wondering, like, do you expect that like accuracy differential to hold on like more complex, larger images, or would you see maybe like existing approaches to do better?
I guess on the real segmentation benchmarks, the problem is we have a lot of occlusion, and the shape priors may not be that useful in that case. And it's often very difficult to set up the problem correctly, so there are all these other aspects of the model that determines whether you get the best results. And that's why we consider this simple segmentation benchmark where shape prior is very important. And, but I think ultimately, once we figure out all the details of segmentation models, shape priors gotta be important, and the fully convolutional approach for solving the problem is gotta fail in ambiguous cases. Now, if you have very high resolution images where there's not a lot of ambiguity, by leveraging a lot of training data sets, we may do a reasonable job with fully convolutional models, but in the presence of ambiguity, priors can help disambiguate the outputs. All right, I guess we have to, do we have to leave the room, or?
In like 1 minute.
Okay.